The engineering design cycle that we decided to go with has 4 steps. So first we had to define the problem. So our bridge had to be self-supporting, span a gap of 4 feet, and collapse into a 1 foot cube box. It had to hold a minimum of 60 pounds and be a max of 8 pounds. With our research, we primarily looked at truss designs and the forces acting on the bridge. So the truss design we decided to go with is a Queen's post truss design. That's like the technical term for it. Then we looked at the forces acting on a bridge. So that could be torsion, compression, and tension. So I'm going to primarily look at compression and tension. This top beam right here is going to work in tension because when you push down on it, it's going to expand. And so this bottom beam works as compression, so it's going to be compressed. So this distributes forces throughout the bridge, that way it can hold a greater amount of weight. So first our group had to come up with solutions to the problem. So we thought of building a bridge using powerful fishing line, and we thought of just making a straight line of blocks that spanned 4 feet and somehow collapse into a 1 foot cube box. But we ended up deciding to go with the truss design because we believed that it would be stronger. So this is the prototypical view of what our bridge should look like. So this is our blueprint of the bridge, and it describes everything that's supposed to be in the bridge. However, not everything that we constructed ended up looking just like our design here. Step 3 involves building and testing the prototype. So we pretty much had to build this bridge and make sure that it followed the requirements that we had to meet. So after we built our bridge and had our design in our head, we had to evaluate the bridge and see where it was at. So with our bridge here, it ended up being 12 pounds when we first constructed it. So we had to take out a bunch of weight from the bridge, and we ended up getting it down to the 8 pounds required. And so our original bridge had space between these 2 members, and so our space between here we had to cut down in order to maximize strength and efficiency. And the placement of these middle blocks ended up being key to our design because they kept our bridge from collapsing in on itself, and it helped it to self-support, while it also helped for our bridge to be more strong and efficient in holding weight.
The advice I'd give to next year's freshmen doing the collapsible bridge would be to 1, start working on your bridge a lot earlier so you have more time with it to work on it. 2, I'd also say do more research so you can get more designs for your bridge so you have more options. And then 3, make sure you test your bridge before the actual day so you can figure out whether it's going to hold the actual amount or not.
During FEDD Day, we finally had a chance to see what other people have built, and we saw many good designs and kind of realized where we could have improved on. About 7 or 8 groups went ahead of us, and about 2/3 of them were able to meet the 60-pound requirement, and only about 1/3 of them were able to hold the max of 135 pounds. And when it was our chance to go, we were able to put together our bridge just under the 90-second requirement. So when we put the bridge to the test, it was able to hold 50 pounds, but when the last 10 pounds were added, the bridge unfortunately collapsed after a few seconds, and it broke at a weak spot on one of the hinges.
If I were to do this FEDD project again, I would have used less wood in the bridge because it was too heavy, and I would have made the bottom beam a little smaller to cooperate with the hinges. I also would not have borrowed wood from the craft center as it was of lower quality than the rest of our wood.